So I'm not going to be picky on the workbook. You don't need to get it anytime soon. In fact, I think at this rate, I'm just going to send you the first 3 pages of it or so for now.
On back order anyway at the bookstore.
Yeah, it's always on back order. Isn't that great? So the workbook, because it's on back order so much, I don't even have it. So you'd think I would want to have it. But then these workbook pages, well, I've been told you can turn them in. Well, at first I was told you could turn them in to me physically, and then I was told you have to turn them in online. So when I shared that folder with you, so hopefully you all received a link to a shared folder. And through that shared folder, that's where the workbook page submissions will go. So that first assignment, whether you've done it, looked at it, or have no idea what I'm talking about, primarily that email will, that email or announcement in Moodle, that will help you figure out what the first assignment is, and that helps you figure out the shared folder. Yeah, email requirement. A lot of you are incoming freshmen. This is normally when I ask who in here is new to Southeastern, and you raise your hands, but this is a different time. So if you email me using a Gmail or something, I'll just respond saying, hey, use your Southeastern address. If you try to do anything through something that's not Southeastern, chances are it's not going to work out perfect. A lot of your phones tend to be already defaulted to your Gmail. So if you have issues, then that might be an underlying issue. Yeah, the workbook pages, blah, blah, blah. Midterm, we can talk about that at another time. We'll talk about that closer to when the midterm comes up. Grade distribution, pretty straightforward. We have homeworks, we have quizzes. Both of those are, well, the homeworks, quizzes, and all the tests are in my math lab. You know, I'm not saying my meth lab, I'm saying my math lab. It's much different. If you go to assignments in my math lab, you will see homeworks are with the blue circle, quizzes are with the, I'm not good with colors, yellow square. Yeah. So that's a thing. And we're going to be going over a bunch of stuff. Don't cheat. I think that's pretty straightforward. Due dates, makeup, face mask. Everybody in here has a face mask. Fantastic. Working from home, you can do all this from home. All that other fun stuff. So that's pretty much the syllabus in a nutshell. It takes all these pages and summarizes it to, I don't know, a few minutes. So yeah, mainly get the calculator, and please get my math lab. Please get my math lab set up as soon as possible if you haven't done so already. So far I've noticed 31 of 37 students have already set it up, which is awesome. That is much better than expected. But other than that, I suppose we'll go ahead and move on to the material at hand. And if you, so upon having my math lab all set up, you will notice under course notes, I have, well, the course notes. This took a while to type up. So yeah, those are accessible, and my class will be completely predicated off of going through these notes in a sequential manner. You can print them out, do whatever. This mainly makes it easier for me because I don't have to write the question, and it makes it easier for you all, so you know what I'm talking about. So let's go ahead and just start off with that. You see this? Yes, I can. So for those of you, well, for everybody here, this first attempt at working this software might be clunky. and I'm already thinking about ways to make it better for the next class period. So try and hang tight with me as I siphon through all this stuff. So upon downloading this, you will see, you scroll down, you will see functions. This is the first section we'll start off with, just functions. Some of you may already know what functions are, but to give you another idea of what functions are, and I wrote a little description here. This was a description I thought about back when I was a tutor years ago. You have a car, and it travels some distance over some amount of time. I think that's pretty much practical to a lot of us. So if I asked you how fast the car was going after 3 seconds, it wouldn't make sense for any of you to give me 2 separate miles per hour that the car would be traveling at one particular time. So the example I have up here, 30 miles per hour, 45 miles per hour. That wouldn't make sense. The car is only going to go one speed. That and to slowly incorporate more technical terms into it, the input of 3 seconds, so the amount of time, can only correlate to one output. Because if the input corresponded to more than one output, then that means after 3 seconds, the car can go multiple speeds. And that's, it's not possible. So this is pretty much the general idea of a function. So for one input, there's one output. If that, there could be 0 outputs as well. For example, how fast is the car going after -1 seconds? There's no output. Is that bad? Not really. That can happen. So function, I throw in some technical terms. Here I call it X and Y, or 2 non-empty sets. That's just kind of some formality. It pretty much says exactly what I said. It associates one element of the input to one element of the output. And the input set, you'll see this word come up throughout this section, but more so in later sections. The input the input set's called the domain, and the output set is called the range. And so those words will come up quite a bit. And also, we normally use this notation. It's f of x here, as it's normally verbally said, f of x, a function of x. We'll see a little bit more what that entails as we move forward. So, as you may notice in the notes have these clear gaps in them. And as you would imagine, the gaps are, well, to make you all pay attention. So this is the part that you fill in. And I fill it in as well. Part that gets clunky is the stylus that I'm going to be using to do so. This might or might not be very successful, so this should be interesting. So for example 1 here, it says state the domain and the range for the following functions. I can do this. Anything. Okay, so let me try something here. So state the domain and the range for the following relations and determine whether each relation represents a function. So what the world does that even mean? And then they give us these things with parentheses and numbers and all of this stuff. So these parentheses with the comma, some of you may be familiar with this. These are called ordered pairs. Ordered pairs have an x value and then a y value. And the domain is the collection of x values. The range is the collection of y values. And I think it's pretty straightforward. Let's find out. What I'm going to try and do instead is view, transparent. Fingers crossed that this works. All right. So we start off with, it says find the domain. And with the domain, it normally has, so you might notice in the premise of example 1 here, there's this curly brace. So that's what this symbol is supposed to represent. And I'm going to just leave it at that for now. The domain is the collection of x values from the problem above. What are the x values? They're the first number in every set of parentheses. So if you see, I'm so tempted to point, but most of you are on Google Meet, so try to get out of that habit. So the domain here, we start listing the x values. So that pair 4 and 5, you just list 4. And the pair -7, 5, we list -7. 8 and 6, we list 8. But 4, we don't have to list 4 from that 4, 16 pair because we already have 4. It's over on the far left. So we're going to close this. So that's the domain. So that's it, just listing the x values.
Is it okay to put them in order from least to smallest, from left to right?
Order doesn't matter.
It does, okay.
Yeah, that's a good question, yeah. Order doesn't matter here, so. And we'll find that out for the range as well. So the range is, well, we're just going to list the y values. So that pair of 4 and 5, instead of grabbing the 4, since the 4 was an x value, we're going to grab the 5. And it just so happens there's another 5 in the next pair, so I don't have to rewrite it. We don't need to write doubles. So I'll move on to that 6 and then 16. So now, so that's the domain, that's the range. Try to close this off. And then it goes on to say, or it goes on to ask whether the relation is a function. And so, all right, what does it mean to be a function? Every input has to have at most one output. So you can think about these numbers as seconds and the output being miles per hour. Well, that might be good because that might not be good because of -7. But the general concept remains the same. Does every input apply to only one output? And the answer is no. Because 4, and those of you on Google Meet, if you notice with my mouse, 4 corresponds to 5 and 4 corresponds to 16. That's the same idea as a car after 4 seconds is going 5 miles per hour, and after 4 seconds it's going 16 miles per hour. That doesn't make any sense. So this is not a function. Where am I going to write this? Not a come on, function. That does say not a function. Again, I'm trying to get used to the stylist, the stylist kind of writing. This is not a function. That's what that part says right there. For question 2, we're going to do the same exact thing. It's just different numbers. So there we go. And click. All right, so the domain, let's try this again. So the curly brace, and we're going to list all the x values. I'm going to go a little bit quicker this time. -3, 2, 3, and 0. Just listing all the x values. The range. We're going to list all the y values. Seems to be 2 8. So 2 and 8. There's another 8 over here, which we don't have to repeat any duplicates. And then I see a 3. So the domain, there were 4 distinct numbers, so we wrote 4 distinct numbers. The range, there was a duplicate, so we only had to write the 8 one time. The question now remains, is this, they call it a relation, is this relation in fact a function? So what does a function mean? Does every input have at most one output? The answer is yes. -3 has its own output. 2 has its own output. 3 has its own. 0 has its own. There's no duplications in the y based off of a particular x value. So this is a function.
It's just the X can't repeat the wrong
It's, I mean, you can have repetition for the y, but yeah, not for the x. Yeah, that's another way you can think about it. So that'll help you with a few problems here and there in the homework. And another reason to get my math lab set up, oops. Another good reason to get my math lab set up as soon as possible is because the first assignment, I think, is due Friday. So please go ahead and get that figured out as soon as possible. So because of the way I'm writing, as you can see, it doesn't carry on with the PDF. So if you are still writing, so that means, of course, I can't continue too nicely. I'm gonna have to erase. But like I said, I'm recording, when I record all these meetings, which hopefully I'm still doing. Yeah, I'm still recording. So I post all of these to YouTube, and I'll post the links equivalently. So as I fly through these, just keep in mind that it's not like these notes are lost forever. So I'm going to erase this. Instead, I'm going to erase this. All right, cool. And I'll move on. So I hate Windows computers. I can't stand them. That's crazy. Okay. So we move on to example 2. Determine whether the function defines y as a function of x. Well, I don't see any points anymore. I just see a lot of algebra looking stuff. Looks kind of gross. So in fact, it's so gross, I'm just going to tell you how to do these. Because there's not really any math that goes into these. It's just an association. So I'll explain it verbally and then apply it to these two. Y is a function of x whenever y does not have a square on it. That's it. So in question 2 here, right here, oh, that's an eraser, right here. Why is it doing this? Pen, please. In question 2 here, there's a square on the y. So guess what? It's not a function. That's it. That's all you have to do. On problem 1 here, I don't see a square on the y. And remember, square means a 2 is an exponent. That's when I say square, that's what I mean. So this is a function. See, that was easy. And for you Google Meet people, you can always just screen capture using a snippet tool, or you could just take a picture of the screen if you don't want to wait for the video to come out. I don't know, that's a thought, because I'm going to erase. And I'm going to move on. So we talked a bit about what makes a function, or what makes an equation a function, but what about how to use those actual functions to construct meaningful new functions or values? And so for example 3, it says, all right, we're given a function, in fact, really, n, yes. So we're given this function here, and it wants us to find a bunch of stuff about it. So in fact, it's got 5 parts. So let's go ahead and do that. Now, 1 second. Yeah, let's go ahead and do that. So f of 4 for the first one. So when it wants you to find f of 4, it means plug 4. So when there's a 4 in the parentheses, that means plug 4 into every x value. So this might be familiar to a lot of you. If not, that's how you do it. And so that's just a bunch of arithmetic from here. 4 squared, 16. 16 times 4 is 64, plus 12, that's, I don't know, 76, 73. I don't know, I'll check my work.
It's right.
That's right?
Mhm.
I've been doing this a long time.
Yeah, I was in the
So yeah, 73. So if you see f of a number, that's all you do. You just plug the number into every x that you see. We had 2 x values in this problem, so guess what? I plugged 4 into both of them. Something that I like to do as a habit is use parentheses to substitute values and expressions in. You'll see it for the remaining parts, but every time I plug the 4 into the equation, I used a set of parentheses. So there is a reason why I did this. It'll make more sense later. Actually, in part B, it'll make a little bit more sense. So here, this is f of negative x. Well, that's not a number. What do I do with it? Well, what's the general idea? If there is something in the parentheses, you replace x with it. Let's go off of that idea. So that will be equal to, so remember the equation is up above, it's that 4, but not x squared, it's going to be negative x squared plus 3 negative x minus 3. So every x that I saw in that function above, every x, I replaced it with negative x. So when I did that, I used parentheses every time I substituted. So every time I substituted a negative x, I used parentheses. And this is what I have so far. But welcome to the world of MyMathLab, where an answer that you give may not be the correct answer, even if it's the answer. I see a lot of you shaking your heads yes, and there's a lot of you at home probably groaning over the mere mention of the terrible sight of MyMathLab. So this answer is not simplified. That's right, one of the bane existences within MyMathLab is simplification. It's not simplified. And the reason it's not is because, well, I guess naturally we can simplify this further. The negative x here that's squared, let's see, I'll point to this without it being a mess. The negative x squared over here negative x squared is x squared. You might think, well, that's not cool. How'd you just get rid of the negative like that? What does a square mean? It means you multiply something to itself. So what's negative 3 times negative 3? Positive 9. Well, that's negative 3 squared. What's a negative times a negative? It's a positive, and that's the same concept that we're applying here. A negative times a negative is a positive, and that's why the thing I have in red is valid. So if anything, I'll simplify that part. So now that's 4x squared. And now we move on to that plus 3 times negative x. But there's no square to really save the negative x. So guess what? That negative doesn't go away. In fact, it's going to just climb to the front. So notice the sign changed. It was plus 3 times negative x. Now it's minus 3x. Because there was nothing to get rid of that negative. So it climbs to the front. And then minus 3, because nothing's really happening there. And that's the simplified form. Maybe tedious, but doesn't that look so much better? So let's keep going. So what about if we unfortunately made this a little bit more challenging? All right, I'll bite. Let's see what we got. Part C is f of x plus 2. And again, that's, well, there's a number, but it's being added to the x. So there's now 2 terms in the parentheses instead of just 1. What do we do? Well, what's the general idea that we've used already? Might need a little extra space here. So that would be equal to, so the equation above is that 4x squared plus 3x minus 3. Every place I see an x, so 4x plus 2 squared plus 3x plus 2 minus 3. So every place I saw an x, I replaced it with what was in the parentheses. Every time I substituted, I used, well, parentheses. So now we have this. But guess what? Because it's my math lab, this isn't good enough. I know, how optimistic. This is not good enough. We need to simplify this. So naturally, we need to FOIL. So foiling, oh, this should be exciting. Let's see how much of this I can squeeze in here. So before we even talk about foiling, what is x plus 2 squared? That's x plus 2 times x plus 2 plus 2. And for the next part, I didn't want to do that yet. No, actually I did. And for the next part, you see the plus 3 times x plus 2. For those of you at home, you'll see it a little, you'll see it here in a bit. Here I'm using red to imply a distribution here. So this is the distributive rule from just standard high school algebra. That distribution, just as a reminder, it tells us to multiply the number in the front to the numbers in the parentheses. So now that I've illustrated that. So 3 times that first x, so that first red arc, 3x. And then 3 times the 2 in the back, that's just plus 6 minus 3. I'm just going to borrow the space for now. I'll come back to that. So let's keep going. Keep going. So those x plus 2's that are next to each other, well, when you have, so those are in factored forms. So with the factored forms, we're going to do something called FOIL. A lot of you may be familiar with this, but if not, FOIL stands for first, which is that first arc that I just illustrated, outer, inner, and then last. So with the 4 still on the outside, we didn't do anything to the 4. We're using the FOIL property to the x plus 2's there that I just drew all the red arcs for. So the first is x times x, which is x squared. X times 2, which is 2x. Plus 2 times x, which is another 2x. And then plus 4. And all of that is still in the parentheses of that 4 that's just been on the outside the whole time. Now there's still that plus 3x. And we have like terms at the end, 6 minus 3. That's just positive 3. Additionally, we can go ahead and I'll illustrate this in red. We can distribute that 4 in the very front as such. Illustrated just like that. So 4 times that x squared in the front, 4x squared plus 8x plus another 8x, because that's 4 times 2x, or 4 times 2, which is 8, with the x remaining, and then plus 16, because of course 4 times 4. I know, this problem's really fun. So let's keep going. Because we have like terms. 4x squared doesn't have any like terms, so we just write down 4x squared. And then in red, use blue. So that 8x, that 8x, and that 3x are all like terms. So 8 plus 8 plus 3, that's hopefully 19. And then we have the 16 and the 3, which gives us 19. That would be our final answer. Fantastic. Let's see if I can fit part B into this small segment here. Good luck to me. So this is f of 3x. And so what's the idea? The idea is we're going to plug in 3x into the original function. Every place we see an x in the original function, we're going to replace it with 3x. And from here, well, the 3x squared But 3x squared, well, what's 3x times 3x? Well, 3 times 3 is 9, and x times x is x squared. The 4 is still on the outside. The 3x times 3x is 9x squared. For the next part, it's 3 times 3x. 3 times 3 is 9. That's just 9x minus 3. Same idea. To finally simplify this, the 4 times the 9 for that first term is 4 times 9. It's 36. 36x squared plus 9x minus 3. And that would be the final answer for part D. But hey, lucky us, there's a part E as well. So for those of you using Google Meet, you may screen capture this right now, or if you don't have the notes caught up, you can watch the video later and you can get all this again. I'm going to erase it. In fact, maybe I'll leave that for those of you still writing. So I'll try and finagle this appropriately. I think I got it. So ignore A, ignore B now. So part E, it said f of, and it had x plus h. And you might think, Brad, come on, you're killing us here. Letter, then a letter and a number, and now 2 letters. Yeah, I am killing you right now, metaphorically. So it starts off the same way. X plus h, we plug that into every x value, or every x variable in the expression. That's 4x plus h squared plus 3x plus h minus 3. Which means, well, we keep going. For the x plus h squared, x plus h squared, we have to FOIL that. What does it mean for something to be squared? That means we multiply something to itself. And then for that 3, red, we distribute like that. So that's 3 times x plus 3 times that h minus 3. And now I don't really have much of a choice. I got to start erasing stuff from before. So you ignore that, we're on problem E right now. So drop this down. And here we're going to distribute just like we did in part C. First, outer, inner, last, just like we did before. Could be an initial point of contingency about what this product may incur. The first in the FOIL, that's going to be x squared. X times h, the outer part, that's xh. And then the h times x, well, that's going to be hx, but you can also write that as xh. That's the same thing as hx. And there's a reason why I wrote it this way. Plus h squared, because h times h. And then we throw everything back in. 3x plus 3h minus 3. Finally, we notice that since I have a little bit more room, I can do this. xh plus xh. Well, those are like terms. That's the reason why I wrote them the same way. That's 2xh. So when you add two things, or yeah, when you add something of the same type together, you're inadvertently multiplying it by 2. And so now we're distributing. I'll do this. We're distributing the 4 to the x squared to the now 2xh and to that h squared over there. So 4 times the x squared, which is 4x squared. 4 times 2xh, that's 8xh. 4 times h squared is 4h squared. Plus 3x plus 3h minus 3. And thank goodness there's no like terms, so we're done. That's one of the more unsightly problems in the homework. So don't think that every problem is completely predicated off of the same sequence of steps as this one. This one's just a hardcore problem. But it does generalize the types of steps required. And yeah, you're more than welcome if you're in class. You could take pictures of these with your phone. People have done that before. That's fine. People in Google Meet, like I said, you can print screen or use a snippet tool to get all this if you want. Or you can just look at the video later, rewrite it. But other than that, we're going to go ahead and erase this and go ahead and move on. Maybe the next time I write these notes, I'll put more space for myself. That would be nice. Okay. We also use something in this class. Some of you may be familiar with it. Some of you may not. It's called interval notation. Interval notation is a compact alternative to using inequalities. So you may notice the inequalities over here where my mouse is hovering over. And yeah, so in this class, we tend to use an alternative way of defining inequalities using interval notation. And I wrote some sort of cliff notes for how interval notation is formatted. It's a compact notation. That's one reason why we use it. That is represented by a pair or pairs of numbers. Okay, so a pair of numbers, let's keep that in mind, maybe like a 4 and a 6. This notation follows these rules. Each number is accompanied by either a bracket, if the number is included, or a parenthesis if the number is not included. Well, we're going to do some examples of this later on. But each number is accompanied by either a parenthesis or a bracket. The smallest number in the pair is always written on the left, largest one on the right. No variables should be in the notation. Only numbers or the infinity notation. See that momentarily as well. Disjoint intervals are glued together using, it's called the union symbol, which is just a U. So with all of these things predefined, let's go ahead and look at the most common application of interval notation, which is domains. So I mentioned domains before. I mentioned them as the collection of all the x values, all the input values. Well, the question we consider is, well, what are the collection of input values? Because not everything can be an input for every situation all the time. For example, dividing by 0. I think that's a universal bad thing. Dividing by 0, unless you deal with a fun topic called projective geometry, is not an applicable operation that we can apply. So that 0 would be excluded from the domain because it would not be an appropriate input. So I like to put everything into as much of a check by check or checklist, sequential process, streamline, whatever you want to call it. I try to put it into as much of a format like that as I possibly can. And this was the best I can do for domains of a function. And they're all enumerated by certain criteria. If you read part 1 or 1 here, if the function has a variable expression in the denominator, so you ask yourself, as you're doing the homework, this is how this applies. This is your thought process. If you're finding the domain of a function, you ask yourself, does this function have a variable in the denominator? If yes, use this, I suppose, process. Set the denominator not equal to 0 and solve for x. Okay, and then I immediately follow it up with a situation of the sort. Example 4 says, find the domain of this random function, which has a variable expression in the denominator. There's a variable right there. Naturally, the criteria tells us is we set the denominator. So what's the denominator? It's x to the third minus 64. X. Set it not equal to 0 and solve for x. That's exactly what the criteria tells us. So naturally, we have we have some basic algebra problem where we have to factor x, and it's a factor-based problem. One of the algebraic properties is that both of these terms, so now once we do this, we're essentially not even looking at the function anymore. So we're not even looking at the function anymore. We're now looking primarily at this association. And so with this factorization problem, one of the things we ask ourselves is, do both terms have something in common? They both do. They both have an x in common. So we can factor out an x. So hopefully you all remember that. We can factor out an x. So when we factor out an x, we're taking an x away from both terms. X cubed had 3 x's. We just took 1 away. Oh my goodness, how many do we have left? 2. And then the minus 64x, well, we took an x away. It's just minus 64. So now we have this. So there's a particular reason why we wrote it in this way. So hopefully you remember, or if not, you should try to remember soon. that if you have a product of things equal or not equal to 0, then we could split up the problem where each factor now becomes not equal or equal to 0. So in other words, each product, so notice I put a dot right here. Now each part is not equal to 0. That's why we factor. This is why we factor. We'll see this again throughout the semester, because factoring is going to come up a lot in this class. We factor because once we find factors, which is the individual parts here, once we find factors, then, well, we can break up the problem into smaller segments, which are a lot more manageable. In fact, lucky us, one of them is already solved for itself. X is by itself. But we're going to have more than one answer, because there's this part on the right here where X is not solved for. Now, you may look at this. I suppose, in other words, an astute student may observe a difference of squares. If what I just said is foreign to you, that's okay. Let's try to get X by itself. Add 64 on both sides. And then we can take a square root. The square root is to get rid of the square on the X. And so now we get that X is not equal to 8 and negative 8. Because whenever you apply a square root, you have to apply a plus or minus sign. So you might think, all right, cool, we have 3 answers. X is not equal to these three things. Fortunately, no, because of course it's my math lab. Good enough never is. So instead, we have to express our answer in interval notation. So we have to express our answer in interval notation. Due to space constraint, I'm going to erase the leftmost part. And so what we found was that X cannot equal 0, 8, and negative 8. So what can it equal? We have the can't equals part. That's so glass half empty. Let's look at glass half full. What can X equal? Well, you would think naturally everything else. What does it look like on a number line? Here's negative 8. Here's 0. Here's 8. We're excluding those 3 values, and everything else is good. Everything in red is good. So what we've now written are 3 disjoint intervals. One interval being, well, the far left here, let me use blue, color blue. The far left stuff over here, what would that interval be? What would be the furthest thing to the left we can go? That's negative infinity. And the furthest to the right we can go seems to be -8. That's right where those blue little dots are at. This is also a part of the idea of interval notation. Every number, so I kind of did something without explaining it. Every number or infinity that you have has to have either a parenthesis or a bracket next to it. Infinity always has a parenthesis, just forever. Just that's something you will have to do for the rest of the class. Infinity and negative infinity will always have a parenthesis. If you ever put a bracket, it's not going to be correct, primarily because bracket means equality. You can't equal infinity. It's not a number, it's kind of an idea. And something Toy Story reference, but you get the point. And so, but -8 is a number, and we don't want to include -8 because we just said earlier that x cannot be -8. So we use a parenthesis on the -8. So every number has to have a parenthesis or a bracket. -8 has a parenthesis because we're not equal to -8. But this isn't just the answer. There's two other disjoint intervals. Seems like earlier I said something about disjoint intervals. So what I said in particular was that you have to glue them together using some cup notation. So that's exactly what I'm doing here. And now I'll go ahead and tack on the next interval. And it seems like it goes from -8 to 0. Why are you there? It just works against me every step.
It slows you down too.
My brain does that to me all the time. Very unfortunate. Can you not do that? All right, whatever. It's there. Doesn't want to go away. All right, so now the interval from, so we left off at -8 from before, so now we pick up at -8. We're pretty much dancing around -8. If you like dancing, then there you go. So -8, and then we go to the right until we hit another issue, which is the 0. 0 is not included, so we use a parenthesis for it. And now we're dancing around the 0. And the 0, we go from 0 to 8 now, +8. And then from 8 to infinity. Again, I picked the toughest one, but it has all the ideas of the easier ones. But this whole elongated thing with these U's and maybe I should, but yeah, this whole expression down here would be the final answer. Yes, the whole thing. The problems in your homework are going to be easier than this one. So just keep that in mind. They're not all like this. This one is just hardcore. All right, so I don't think I have to erase anything yet. We move down to part 2, which is thankfully much easier than part 1. So this one talks about finding the domain if you have a square root. If you have a square root, what it says is set the radicand greater than or equal to 0. What the heck is a radicand? Sounds like a Pokemon. It's a radicand. So a radicand is everything under the square root. All right, so it says set the radicand. So what's everything under the square root? Which is 4x minus 16. What does it say to do with that? Set that greater than or equal to 0. Greater than or equal to 0. And solve for x. Okay, well, the inequality looks pretty straightforward. We can solve for x pretty easily here. Add 16 on both sides. divide by 4, and then we get that x is greater than or equal to 4. But of course, good enough it never is. We have to put this in interval notation. So here we have an inequality. X is greater than or equal to 4. So I'm going to do what I did before, establish the inequality part. I'm going to think about this on a number line, just like I did before. Let's see, 4 is the significant number here. It seems like 4 can be included because we have an equal to part. So I'm going to fill in this circle here at 4. And since x is greater than, well, what's something greater than 4? 5. Where's 5 at? It's over here. So that stuff in red is the interval in question. There you go. That stuff in red is the interval in question. So how do we write this in interval notation? Well, what's the smallest number in this interval? It's 4. Is 4 included or excluded? It's included, so we use a bracket. And then what's the furthest to the right? It just seems to be infinity. There's no number there that's specified. And infinity always has a parenthesis. Oh my goodness, I'm actually on time. I'm pretty shocked about that. All right, so I suppose, again, if you're copying this, I'm about to erase it, so take a picture, take a screenshot, do something, or watch the YouTube video. All right, so how does erasing work again? With eraser, like stuff. All right, cool. So click, down. There's another criteria. So we talked about criteria for finding the domain. One of them was, well, what happens if you have a variable expression in the denominator? One of them is what happens if you have a square root somewhere. And now the other one is pretty much the metamorphosis of the two. What happens if you have both something in the denominator, a variable in the denominator that has a square root? So it's pretty much the final boss. And so what you do here, well, I give you the criteria for this as well. Criteria being set the radicand, so I'm using that weird word again. Set the radicand strictly greater than 0 and solve for x. So although this one is predicated off of more things, it actually works out a lot easier than the first condition that I had. So it says set the radicand strictly greater than 0 and solve for x. So what's the radicand? I mentioned earlier, that's the thing under the square root. That's the thing under the square root, and this problem here is just x plus 9. And it says set this strictly greater than 0. So strictly greater than 0. And solve for x. Hey, that looks pretty all right. There we go. Well, just subtract 9 on both sides to get x by itself. X is now greater than -9. And, well, of course, maybe it's not good to establish a philosophy of good enough never is, so maybe I shouldn't say that anymore. But we do have to put this in interval notation, which means I'll do what I did before. Here's the inequality in question. That should be 9. I'll go ahead and put this on a number line, because it helps me try to convert this to interval notation. And let's see, what's the significant number in question? Seems to be -9. X is, well, before I say that, is -9 included or excluded? It's definitely excluded because we don't have an equal to part in the inequality. X is greater than -9, which means we need to shade to the right, because that's where all the greater numbers are at. And finally, we go ahead and use this illustration to help determine the final answer. So in that red interval I just shaded, the smallest quantity is -9. It's all the way on the left. So and I use a parenthesis for -9 because -9 is, well, not included. What's the largest quantity in this interval? It's positive infinity, because when you go to the right, well, there's really no bound. There's nothing to really restrict it. And infinity always has a parenthesis, and that would be the answer. And this is the criteria you would use if you have a variable and expression in the denominator, and that thing in the denominator has a square root. And finally, oops. And so what we will conclude with is the final criteria, which actually we don't do anything here. So if the function doesn't follow any situation above, so I gave 3 conditions, then the domain is, and I just tell it to you. It means we didn't run into any issues. Everything passed. Think about it as a checklist. So all real numbers. And we normally notate it as -infinity to infinity. So that is all I have for today. For those of you, I think there was one question I saw on Google Meet. I'll answer that in a second. Classroom people, any questions about anything?
I have one question. Our Unit 1 assessment is going to be held according to the calendar, or the first test is going to be, is that September 3rd to the 4th? Am I looking at that right?
Yeah, so September 3rd to September 4th. So you take the first assessment whenever you want.
Okay, and then that's going to cover everything that's here, all
Yeah.
of this.
Yeah, everything that I have in the notes right now.
Okay,
So everything that's up in the notes right now will be applied to the Unit 1 assessment,
okay, perfect.
which you do not have to take here. You can take it wherever you want, whenever you want.
So we can take it here. if we want.
Yeah, you can take it here.
Okay.
It's unproctored, in other
I've had
words.
a really bad experience with property, so kind of.
Well, you'll definitely have to use it for the final, unfortunately.
In a way, kind of. I'll explain later.
And you might have to use it for the midterm. Fingers crossed we don't move to remote
Yeah.
delivery. Well, just fingers crossed that a pandemic doesn't go absolutely berserk. I
Well,
feel like we can all agree on that.
I-
But yeah, for the rest of you, if you don't have any other questions, good to go. Online people, I guess I'll, one question before us at the beginning of the problem. Okay. We'll worry about it next time.
Notes or more.
The notes are in my math lab. If you, so once you follow the, have you set up a my math lab account? I just added a tab called course notes. You can find everything there.
Yeah, Fridays, we do that virtual, right?
Yeah, it's all virtual Fridays.
And Wednesday, we do virtual.
Yeah, so, okay, so what happened to the 4x at the beginning of the problem? That's a good question.
Thank you so much.
Yes, certainly.
I can already see it's gonna be a lot better experience. But, I kind of did have a question. You're not still recording, are you?
I was wrapping up. There's someone who asked, what happened to the 4x at the beginning of the problem?
I'll ask them.
Okay.
Thank you.
And Molly, I can answer your question right quick. Attendance is already recorded with Google Meet. By you just showing up, it already recorded your attendance. So that should answer that. And then the 4x thing. So I hope I didn't miss something. Let's see. What am I trying to do here? What happened to the 4x? Oh, okay. That's an easy one to answer. Yeah, so to answer your question about what happened to the 4x, we didn't need it. The criteria, what the criteria said was just take everything under the square root and set that strictly greater than 0. So by virtue of that, it means that everything else in the problem was completely irrelevant. So anything could have been in the numerator there. That 4x was there in this problem. Could have been anything. But by virtue of the problem, it said that the only significant part relative to what we're trying to find is is in the radicand, and specifically what we do with it. So hopefully that answers your question.
You teaching 151 again this hour? Okay, yeah, see? She's got my room number on there.
Oh, gotcha.
Yeah, and then the camera didn't even work. They had to come over and put a new camera in my thing.
Oh, boy.